Yeah, so today I am going to deliver the fourth live session in which I will interact with students about some specific things like Stokes law and some things. So I am SRIPAN. I am working as a PMRF at IIT Beju. So this is one of the deliverables of the PMRF scheme. So this is the fourth week of the live session. So okay, we can start now. So this is the first question we have is choose the correct informations about Poiseuille's flow. So velocity is time dependent. Force due to gravity is considered. The trajectory formed by the forwarding fluid layers at an instant is a plane perpendicular to the flow direction. The trajectory formed by the forwarding fluid layers at an instant is a parabola perpendicular to the fluid direction. So, Sumit, can you tell me which are the correct options or informations regarding Poiseuille flow?
Number 4 is correct.
Number 4 is correct. So,
Mhm.
yeah, okay. So
And
basically, what happens in Poiseuille flow is so these are viscous flows, right?
yes,
So the more we go in the middle of the container, the more the velocity is increasing, right? And as we go to the walls, due to the no slip condition, the velocity will decrease and eventually go to zero, right? So what we get is, if we consider this forwarding heads, we will get a kind of parabola, right? So this is what
yes,
you are suggesting. Okay. So if 4 is correct, then 3 should not be correct, right? The plane, it
3
cannot be
should
a
not be.
plane. Now the
Yes,
two things is velocity is time dependent or force due to gravity is considered. Now when we write down the Poiseuille flow, first of all what we write down is the sorry, rho. So we have viscosity. So the starting point has to be the del V del T
del T.
plus rho. I mean the total equation which we know as
Yes,
Navier-Stokes equation is V dot grad V, right, equals to minus grad P
that P,
plus rho G
rho G,
plus mu
mu del square V.
grad square V. Now the Poiseuille equation is like this second term will be there, rho
Yes,
V dot grad V plus gradient of P will be there, and that is basically mu grad square V, right? So this term is cancelled out, right? This is going to be 0.
0,
So this term is cancelled out means this del V del T has to be 0.
0.
Now if this is 0, then velocity cannot be time dependent, correct?
Yes,
So this is not a correct option. Another thing is force due to gravity is considered. Now to
no,
here you see this rho g is also going to be 0. So this should not be a considered point, right? And
yes,
also this is not correct. So only this last option is correct for the positive flow. Fine. Okay. So I think it's clear.
yes.
Okay. The next question is, so recall about the microscopic description about coefficient of viscosity, right? So mean free path of a fluid. Now first of all, let us recall about the microscopic description of coefficient of viscosity. So basically, whenever we are writing the viscosity term, we are writing this grad square u. Now we don't have information about this mu in the macroscopic scale. We just know about the some value of mu, right? What we have from our observation is grad square u, and this is coming from somewhere, we don't know it, right? But whenever we are going to the microscopic description, we can think of it as intuitively that there is two layers which are successive to each other, right? There is some velocity gradient in between them, and there is some viscous coefficient, right? Now what this viscous coefficient is actually is, we can think of some rubber bands, right? Rubber bands which are joining these two layers. Now it tells us that these rubber bands are basically carrying out some information of the velocity from one layer to the other layer. Okay, now if this is the case, and also we can think of mean free path, that is the path traveled by the molecules between two successive collisions, right? Now let's say these two layers are at a distance of lambda. Fine. Now if this is the case, we can find out that also there is a velocity, let's say v, right? And the RMS velocity is v RMS, and the flow density is, let's say, rho. So we can find out a relation like 2 rho, just a second, this should be 2 rho v RMS, and there should be a lambda, right? So this is how the mu is defined from microscopic description. Lambda is the length scale over which two successive layers are there. Vrms is the velocity with which the flow is moving, and rho is the density of the fluid. Fine. Now what we have, another thing is the lambda, right? The mean free path also has some dependence, like let's say there is a proportionality constant, so it will depend upon the d square, which is the diameter of each molecules of fluid particles, and also it depends upon the n by p, which is the number density. Now just if you just multiply this number density by some mass, that will give you the rho, right? So from here you can find out lambda is basically d square this way, right? So lambda is inversely proportional of d square and rho. Now the question is suggesting that the mean free path of a fluid is increased to 5 times, right? So let's say you have a lambda 1 and you have a lambda 2. So it is telling that lambda 2 is 5 times lambda 1. Okay. So, and this is changing in such a way that the diameter or the dimension of the fluid particles remains unchanged. Now if the diameter is remaining unchanged, the d is constant, right? So from this equation what you get is lambda rho, that is a constant. Fine. So even though the lambda is changing, so you have this lambda rho has to be constant. Fine. Now if you consider the ratio of mu1 and mu2, you have this lambda 2 rho 2 by lambda 1, sorry, this is lambda 1 rho 1 into v RMS square by, sorry, this is not a square, this is 2 and this is v RMS 1. Okay. Now as d is not changing, so lambda p is constant, so these two will be cancelled out. Fine, because lambda 1 p rho 1 equals to lambda 2 rho 2. Okay, so what else we have is v RMS 2 and v RMS 1. Now you know this v RMS, right, that is proportional to root of a t. A t is the temperature, correct? Now the other thing is simultaneously the temperature increases to 2 times of initial value. Comment about the change in the coefficient of viscosity. So what we have is there is a root over, let's say this is T2 by T1, Okay, so as T2 is 2 times T1, so you have mu2 by mu1 is just root 2. Okay, Sumit.
Yes, yes, got it.
So let's say we don't have this information like d squared is going to be conserved. Then what we have, we cannot consider this lambda to rho 2 as constant. So in that case, we have to calculate in a very wise manner. That let's say d is also changing, lambda is changing, then rho can also change. So in those way, you have to be conscious about the problem. Here we have d is constant, so lambda rho is constant, irrespective of the change of the mean free path. So we only have the change from the temperature change, and that's how we are getting mu2 by mu1 is root over 2. Okay,
Okay.
so if we go to the next question, yeah, so this is just the solution what I am telling. Now the next question is, consider a smooth solid metallic sphere moving through a fluid. Now the Reynolds number is 0.1. Okay, now first of all let us recall what is Reynolds number. Okay, so Reynolds number tell us the, let's say Re, it tells us what is the, what Reynolds number tell us.
It tells us the ratio between the first and the third term in the Navier-Stokes.
Yeah, so basically we have the inertial term, right?
Yes.
Inertial
And the viscous term.
term and the viscous term. Okay, just a second. So this is the ratio of inertial term and viscous term. Now it is telling, the question is telling that you have the Reynolds number as 0.1, right, which is quite low. So if it is 0.1, then viscosity is quite high,
High.
right? High
Yes.
viscosity is viscosity. Okay, now if it is highly viscous, then there will be sticking, right? So this is correct option, this is not incorrect. Fine. And the total energy of the fluid will be exactly conserved along a streamline. So is it true?
The total energy, this is true,
Yeah.
but then from the Reynolds number, I cannot relate this to Reynolds number.
Yeah, this is true, because yeah, so it's basically telling that if it is highly viscous, then there is some dissipation of some part of energy, let's say kinetic energy, but the total energy should be true, sorry,
Okay.
should be conserved, right? The third thing is, the drag experienced by the sphere will be proportional to the relative velocity between the sphere and the fluid. And the last one is this proportional to the square of the relative velocity of between the sphere and the fluid. So if we just write it like this, so let's say we have a force like Fd, it is telling this is Fd proportional to u, and this is telling us Fd proportional to u square. So which one of this is correct, right? So as we in the highly viscous region, which is the low Reynolds number, so we see for that we have the Stokes law, right?
Stokes.
Stokes law. Now in the Stokes law, what we have is this Fd is some 6 pi eta or mu in this case, let's say, let us denote it by mu, and then the radius of those particles and the velocity with which it is moving, right? So this is your force for the low Reynolds number fluid. So in this you see this FD is proportional to U, right? So this might be a correct answer, is not it?
This is the correct answer.
Sorry, it's not a correct
The,
answer.
not
Just I mean it's correct obviously, but this is not
yes.
incorrect. Okay. So
No.
the first one is correct, second one is correct, third one is correct, but the last one is not a
Not
correct
correct.
answer. So this is the incorrect option. Okay.
Yes.
So just a second. Let me write. So it's now if we move on to the next question. Okay, just a second. This is just here, just here. Okay. Now the next question is, you have an incompressible fluid which is flowing through a cylindrical pipe. Now its velocity is 0.01 times of the local acoustic speed. Acoustic means sound speed. Can we estimate its dynamics using hydrostatic approximation, or total hydrodynamics equations are needed to be considered? So first of all, we need to understand what is this velocity ratio. So we know about the Mach number, right? M. Now Mach number gives us the ratio between the flow velocity and the local sound speed, which is CS, right? So this is given as 0.01. So this is basically a subsonic flow in which the velocity is very much lower than the local sound speed. Now in this case what happens is we can neglect that change in the velocity, right? That del v del t, since v itself is very much small than the sound speed, which is a characteristic speed of the medium, so del v del t can be tends to 0. Okay, now if t tends to 0, what does that mean is you have the hydrodynamic equation in the form of Euler equation or the Navier-Stokes equation, and in that, like Euler equation, if I write down the Euler equation again, so you have rho del v del t plus again rho v dot grad v equals to, it's a minus grad p plus rho g. Okay, now you have this equation. So what it suggests is that this velocity is very much less than the local sound speed. So in that case what happens is we can consider this del v del t to be 0. Fine. Now if we don't have any information of change in the velocity with time, so we are basically in the hydrostatic approximation, right? So we don't have any dynamic term in this. We only have some change in the velocity with spatial dimension, and also we have some force, right? But we don't have any change in the velocity with time, even though there are some forces acting upon the flow, right? So the flow is there, but the velocity with which it is moving, that is not there. So we can consider that okay, the total there is no change in the velocity due to the time, so we are in the hydrostatic regime. Fine, we don't need to consider the total hydrodynamic equation. That means we don't have to consider the spatial as well as the temporal change of the velocity here, as the velocity is very much lower than the local characteristic speed, which is sound speed in this case. Okay, Sumit.
Yes, yes, yes.
Yeah. So yeah. Now the next question here is so you have a fluid having speeds of 10 times of local sound speed. Now this time the speed is quite high than the local sound speed, and it is suddenly changed its velocity to 0.01 times of sound speed. Now, is the transition scenario a linear regime or non-linear regime? So first of all, what we need to understand is that initially the speed, right, initially the Mach number, let's say m1, which is quite high, right, this is 10 because this is the v by cs, right, and the second by after the transition it is 0.01. So initially it is greater than 1 and then it is less than 1. So what does that mean is initially you have a supersonic flow and then you have a subsonic flow, right? So you have supersonic flow and subsonic flow. Now it is changing from supersonic to subsonic. Some transition is there. Now how do they go through this transition? So can you tell me what is a shock? How shock is formed?
Shock is a discontinuity.
Mm-hmm.
It's not there in the lectures yet. I'm just using my past knowledge of shocks.
Mm-hmm.
So there's a discontinuity in let's say the density,
Okay.
and there is discontinuity in the pressure.
Mm-hmm.
The other one is there is a discontinuity in the velocity. So that is the definition of shock that I remember. I'll have to revise
Okay,
this
so there
concept
is
once
some
again.
change in the velocity, right? As the shock is
Yes.
progressing. That is what
Yes.
we are seeing there. That there is some flow which is going with some subsonic speed, sorry, supersonic speed, and the velocity is changing, right? So,
Yes.
there might be some transition due to this shock, right?
Yes.
Okay. Now, uh, now what is the linear and non-linear regime is, let's say you have some wave is propagating like this. Okay, so you have just a continuous profile of some wave, right? Now wave means some perturbation in the homogeneous or the equilibrium medium. Fine. Now let's say if somehow this is the amplitude, right? This is the amplitude of the wave, this vertical lines. Now if now to have this kind of a continuous shape, what we have is at each point of this profile the velocity will be same, right? Otherwise this shapes will be distorted. Now in case of shock, how the shock is formed? So basically if you have this amplitudes as quite high, okay, this is quite high amplitudes, let's say. So in this case what happens, at some points this the velocity at this point and the velocities at this points, okay, they are not same. Fine. Now what will happen is the velocity at this points will be very much higher than this point. So what will happen, if this profile is there, the next profile will be like a steep gradient, right? Because this is not moving at a much higher speed, this is very slow and this is very fast, so it will catch up with this thing, right? So the profile will change with some steeper gradient. Fine. This formation of this TPR gradient is basically the shock formation from the wave, and that is due to the higher amplitude of the wave. Okay. Now if there is the higher amplitude, that should not be the linear regime. As soon as amplitude is very much high, it is going to the nonlinear regime. Fine. So by nonlinear regime, what I mean is, let's say you have some input, you have some output, right? So basically whatever you are calculating, that has some input in terms of some parameter, and you are calculating some other parameter as an output. Now if your input is changing by some means to, let's say, 5 times, that means your output will also change in that fashion. But in case of nonlinear regime, you have an input, you have an output, but they are not linked with each other in this way that the change in the output is not only depending upon the change in the input. Okay, so that is the nonlinearity thing. And here, when the shock is forming, the nonlinear effects are coming due to the high amplitude of the waves, and finally they are forming the shocks, which will be a transition layer through which or across which the fluid flow will have different velocities. As you said, that shock is can be responsible for some drastic change in the velocity. Okay, I think that's fine, right?
Yes, yes, understood. Yeah.
Okay. So, okay. Okay. Though, so the next question is here. The next question is, consider a solid sphere inside a fluid having high Reynolds number. Now this time the fluid has a high Reynolds number. Okay, so choose the correct statements. Again, we have to understand, or we have to recall the Reynolds number, right? Now when we write down the Reynolds number, it is like BL by mu or eta. Okay, this is the viscous term, and this is the term coming from the inertia term. Okay, so now it is saying that this is a high Reynolds number. That means your viscosity, this mu, is small, right? Mu is small.
Yes.
Now here are some statements. You have to find out the correct statements. So first one is, coefficient of viscosity is high near the surface of the solid sphere. So you have some fluid here, and which has some high Reynolds number, and you have immersed a sphere in between, and it's saying that coefficient of viscosity is high near the surface of the solid sphere. Now that is not a correct option, right? Because we see in the bulk the coefficient of viscosity is very much small because the Reynolds number is very high. So this should not be a correct statement. Correct?
Yes.
Yeah. Now the second thing is, the coefficient of viscosity is quite small everywhere, but the term mu grad square u, where u is the velocity in the Navier-Stokes equation, is important, significant in a thin boundary layer close to the solid surface. Now what happens is, when you have a sphere and you have viscous fluid, so first of all, if it is in viscid, what will happen is, there is a boundary condition which tells us that there is no velocity in the perpendicular direction, right? This is 0. But here you see, when you have inviscid fluid, you have this V parallel or V tangential cannot be zero, right? There is a finite tangential velocity when you are considering the in viscid fluid, but when you are considering the viscid fluid, you are considering that sticking, right? So to have sticking, you should not have any velocity in the tangential direction also. So for viscous fluid, no tangential velocity, right? So if there is no tangential velocity, so what will happen is, so just above this layer you have a tangential velocity, but just at the sphere, at the layer which is touching the sphere, there is no velocity again. So you have this change, this du is very high, right? Very
Hi.
high. And over which this is changing, this is very low, right? Because the dy is very small. So du dy
Yes.
is basically very small, high. That
Very
means
high.
the second order derivative is again very high. So that means this mu grad square u is becoming important or significant in this thin boundary layer close to the solid surface, right? So this is a correct statement. Now the fluid will stick to the surface of the solid sphere. Again, this is viscous fluid, so there should be sticking, right? So this is also correct. Now,
It is not a viscous fluid, correct? Because the Re is very high.
see, the first thing is, whatever the Reynolds number is there is
Hmm.
some amount of viscosity, correct? You cannot.
Okay.
This is clearly not in viscid. Fine. This tells us that the viscosity is very much small. That should not mean that viscosity is not there. Correct.
Okay. Okay.
Yeah. So fluid will definitely stick, but that amount of sticking will not be very high.
Okay. Okay. Okay.
Okay.
Got it.
Yeah. So if 2 is correct, then 4 cannot be correct.
What cannot be
Right.
correct? Yes.
So 2 and 3 is correct. Okay. Now the next question is here. So suppose a ship of the size of Titanic is moving in the sea. Okay. Now can we estimate the drag force acting on it by some setup in laboratory, provided we have the information about the ratio of the inertial term and viscous term? So Sumit, can you answer it?
This, yes, as long as the ratio, that is the Reynolds number and
Mm-hmm.
inertial term and viscous term in both the setup is the same,
Mm-hmm.
then all the behavior of the miniature version of the ship will be the same as the large ship.
So can we do this experiment with water itself?
No, you have to change the fluid. You have to take a different fluid which has a
Mm-hmm.
different viscosity to maintain the
Okay.
same Re,
Okay.
Reynolds number.
Yeah, absolutely correct. So this is the answer for this. So this is known as dynamic
Dynamic
similarity.
similarity.
Okay. So the next question is, what happens to the drag force on spheres with increasing radius size? Whether the drag force is constant across all sides of spheres in a fluid, whether this will increase with size of sphere, Whether this will decrease with size of sphere, or we cannot tell about this thing. What do you think about this? You have a drag
I think it
force.
will increase because the drag force is proportional to
Yeah.
the
So
area.
when we write this F equals to 6 pi some eta, right, rp something like this, so you have a radius, right?
Yes.
So if F is proportional to r, that means if r is increasing, that means this force is
If
also
increasing.
increasing, right? So
Yes.
this will be the correct answer. Okay, so so okay. Now the next question is here. The second, yeah. So the next question is that consider a planetary atmosphere of fully ionized hydrogen which is vertically stratified under the influence of a gravitational acceleration g. Choose the correct options. So first of all, let us try to understand what is this vertical stratification due to gravitational acceleration cause, right? So again, this is about the forces and its implication, right? So what we basically have is F equals to ma, right? Again, now so whenever we are doing some calculation for the sake of simple things, what we do is we consider the steady or equilibrium states. Okay, now if we consider the steady or equilibrium state, what we have is that the change in the velocity should be zero. There should not be any uh, acceleration. Okay, so the force acting on in the entire atmosphere should be balancing each other. Fine. Now the here we cannot we don't consider the effect of viscosity initially. Okay, what are the forces we are considering is, first one is the grad p and the rho g. Just think about the Earth's atmosphere, right? There is a pressure gradient between the higher heights and lower heights, the sea level, and there is a gravity force which is acting vertically, right? These two forces are only there. Even though you have some viscosity at some lower scales, we are not considering that lower scale, we are considering the bulk scale, and in which this is clearly inviscid. Okay, now using this equation, what we can do, if we have, let's say the vertical height is, let's say, z direction, so we have dp dz which will be rho g. Now how many unknowns we have? We have pressure, we have rho. Now again, there is some ideal things that if p is rho kt by m, right? This is your ideal gas law equation of state. Okay, now if we put this dp dz equals to, let's say you are taking this, you change this rho from this, so you have mp by what, kt, right, and g. Sumit, are you understanding?
Yes. Yes. Yes.
Yeah,
Yes.
so you have this equation, so you have dp by p and you
Mhm.
have
KT, N
mg
by
by
KT,
kt dz,
DZ.
right? So from there we can have ln p. On integrating we will get
Mm-hmm.
ln p. Now this ln p will have, if you just have, sorry, if you just have the limits, let's say you have know that p naught will be the value at the lower level and you have some value at some height, let's say pz. Okay, this equals to what? Mg
MG
by
Z by
kt,
KT.
and there is a z,
Z.
right? So
Yes.
let's say for the time being what we are doing is, yeah, so mg by kt. So fine. Now if we write down here that, just erase some parts here. Okay, now from here we can find out that there is this p. If we write the p, then that means you have
E to the power.
e to the power mg by kt and some z,
Z.
right?
Mm-hmm.
Okay, just a second. There should be a minus term somehow.
I think the direction of Z is going to be minus Z, right?
Yeah, yeah, yeah,
Because
yeah.
we are going upwards
Yes,
against
yes, yes.
gravity.
So yeah, so there should be a minus, right? So this one will be a minus here. So this p equals to, basically you have a p naught. If you just change it to, I mean
Yes.
ln from p, then you will
Hmm.
get this p equals to p naught exponential minus mg by kt z, right? So from here again, every time we are talking about the gravitational scale height, so this is how gravitational scale height is here. You
Mm-hmm.
can just change this z by h. Okay, this h is basically your kt by mg. Okay, now remember one thing, that you have a temperature, right? And you are going in a direction vertical in the atmosphere. Now whether the temperature will be isothermal or homogeneous, or it will have some change with the change with height, right? So basically what we have, this t is your
T of Z.
z.
Yes.
Now in that case you cannot just write in this way, right? Because
Mm-hmm.
what you have is a integration over this part, correct?
Yes.
So if we just write it, so what we have is, okay, so we have, let me write in a fresh, so ln p, this should be pz, and there should be a p naught. This is minus mg by kt z, as t is a function of z. So this is dz, right? Now what we do is this pz is, now here there should be, sorry, this entire thing should be there. So dz, there should be an integration of 0 to
Z.
z, right? So this pz is basically a p naught exponential of exponential of minus this, right?
Yes.
0 to z mg
By KT.
kt say Tz. Okay, so this is your more general equation. Now if we put T as isothermal, then we don't need to calculate this much, right?
Yes.
It will just come out this, where you
Constant.
see that the pressure is decreasing with height in an exponential manner. For T is
Constant.
isothermal. Okay. Now if we know the P, you can find out rho also, right?
Hmm.
So basically rho is that from the first equation. So P is rho kt by m. So this is just mp by kt, right?
KT.
Now if we look at this, you see that you have P as this P naught exponential minus z by h, right? So okay, let me take the new page. I think it will be better. Yeah. So what we have is this P as P naught exponential minus 0 to z mg dz by
KT.
h t z. Okay, now we are saying that Tz is basically T for isothermal case, and we have this rho as mp by kt.
KT.
Okay, now if we just change this, like in this equation, what will happen? So you have this rho is proportional to P
P.
by T,
T.
right? So let's say again, sorry, it's better to use this because we have information about P. So it is P equals to proportional to rho T, correct? So we have two things, P and rho naught. So what we have is from P you can write this rho T at Z, right? This is a Z height, right? This is equals to what? Rho naught T naught, right? Let's say for more general case, this is rho naught T naught. So this will be then what? Exponential, again the same thing, right? This one, fine. So you see, if we write down is in this form, you have rho at Z, and that should have this rho naught T naught by T at that particular height, right? And you have this exponential, fine. Okay,
Yes.
now for isothermal case, what will happen? This T naught and T at any height will be equal, right?
Equal.
So for isothermal case, what will happen? That T naught by Tz, that should be 1,
1.
fine. So in that case, rho z is basically again similar to the profile followed by the pressure,
Pressure.
right? This will be exponential and in bracket the everything. So now the first option is, for isothermal atmosphere, both pressure and density falls off exponentially with increment in height. So this is correct, right? Because for
Yes.
isothermal we don't have T by Tz. Now second is, the for isothermal atmosphere, pressure falls off exponentially with height, whereas density falls off as 1 by height. So this is not correct, right?
Not correct.
Yeah. So the third one is, if T increases with height, the density decreases faster than the pressure with height. So density decreases faster than the pressure with height if T increases with height. So let us look at this. So what we have is T is increasing with height, right? So when we consider about P, we have only this exponential thing. Okay, again
Mm-hmm.
when we come to rho, you have that exponential thing again, but you have the temperature in denominator also. Now if
Yes.
this T is increasing, this Tz is going to increase. So what
The
will
row set
happen?
will come down.
That will also diminish this value, right?
Yes.
So we have two contribution. One is from exponential, another is 1 by t. Both of them are trying to drop this, right, rho z. So obviously this rho will be diff more higher than
Then P.
the p, right, for the increment in height, sorry, for the temperature increment with height. Okay, so
Yes.
yeah, so the third one is decreases
Correct.
faster. This is correct answer. Now it's telling that if t decreases with height, the density increases with height. Is it true? So now the t is decreasing. Okay, so again, let's say now you forgot about the pressure, you have only the temperature term. So now you have this rho z equals to this term, right? You
Mm.
have contribution from two things. One is this exponential. So exponential, irrespective of the change of the temperature, whether it is decreasing or increasing, it will decrease your value, right? Okay. So
Yes.
and you have a tz, which is this time, which is increasing, right? This is,
Increasing.
this is
Decreasing.
decreasing. Now if it is decreasing with height, so what will happen? This tz is decreasing, so this will increase, right? So now there two terms, the exponential is trying to decrease the density, and you have a t z which will increase, right?
Yes.
Now what will happen? Now it will depend upon their compatibility, sorry, the comparison between them, whether this exponential term is more efficient than 1 by t, or 1 by t is having a more better or more greater value of respect to this exponential. Okay, depending upon this comparison, we can have the density decrement as well as increment with time in local regions. Okay, so we cannot tell blindly that if t is decreasing with height, the density will be increase with height. Okay, so it depends upon that comparative study between these two. Okay, if t 1 by t is greater or having greater contribution than the exponential term, obviously, so t is decreasing with height, so 1 by t will be increasing, so the density will increase with height. But if this 1 by t has lesser contribution than the exponential thing, so obviously whether, even if the t is decreasing with height, the density must be decreased with height. Fine. Okay,
Yeah. Yes. Got it.
so this is not a correct answer.
Not a great answer.
For
Yes.
this is 1 and 3. These two will be correct. Okay?
Yes.
Yeah. So, yeah. Okay. Fine. Now we have another question here. So, okay. Again. So you have a solid metal ball which is falling in a long liquid column and has attained a terminal velocity of 4 meter per second. What is the viscosity of the liquid if the radius of the metal ball is r equals to 5 centimeter and its density is 8050 kg per meter cube? Now the density of the liquid is given as 1000 km per meter cube and the gravitational acceleration is 10 meter per second. So the question is asking for the viscosity of the liquid. Okay, so what we have is you have a vertical column like this, okay, and you have some solid metal ball which has a downward motion. Okay, so if we have this kind of a thing and you have the liquid as some viscous liquid, right? You have some viscous liquid. Okay, let's say this way, liquid is there somehow. Okay, now what are the forces will act? First of all, it is a vertical motion, so you have a force due to this mg, okay, the gravity. Second thing is there is a buoyancy force, okay, buoyancy. So initially these are two forces. So no, sorry, first of all, when we are putting the ball in this liquid, so it has only one force, which is the gravity, due to which it has a downward motion. And when it is immersed in the liquid, so there is a upward buoyancy force also, which will act just opposite to each other, this gravity force. Now the velocity is increasing. As the velocity is increasing, it will have a drag force, right? And what a drag force do? Drag force oppose the motion, right? So again, as let's say velocity is increasing, so your drag force comes into play as per the Stokes law, right? So you have a drag force. Now what we have? You have three forces. One is buoyancy. The spelling is not correct, obviously. But drag force, and these two are balancing by mg, right? Now if this is balancing, then what will happen? So initially the buoyancy and mg, in these things the mg is greater than buoyancy, so there is a downward motion. Now after that there is a drag force going upward as the velocity is reaching a finite value. So there is some force imbalance, and as the force imbalance is there, there will be some accelerated motion and the velocity will keep increasing. And if the velocity is kept increasing, the drag force will increase, right? So at certain point, as the buoyancy initially is very much low with respect to the gravity force, so as the drag force is increasing, as the velocity is increasing, so buoyancy plus drag force at certain instant will just will be equal to the gravity force. So then the net force acting on the solid metal ball will be 0. Okay, now if there is no force in some body, then what will happen? That should not have any acceleration, then that will continue to move with the velocity attained last in its acceleration phase, when the forces are not counterbalancing each other. Okay, so the last velocity with which the ball will flow down, deep down in the liquid, that is called the terminal velocity. I am not going to do the I think in different lectures that can be done, So right now what I am trying to do is we have a uh, equation for this terminal velocity, which is 2 by 9 eta. You have a r square, which is the radius of the ball, and you have this rho minus sigma, okay, and g. Fine. So this is the terminal velocities formula, where g is obviously the gravitational acceleration, r is the radius of the ball, eta is your this mu, the same thing, viscosity of the liquid, eta on mu, and rho is your density of the ball, okay, and sigma is density of the liquid. Okay, Sumit?
Sorry, I was on mute. Yes, I'm getting the point.
Yeah, so I think the derivation can be done in the lectures maybe. I just want to tell about this dynamics, how the forces are acting, and when the ball will attain its terminal velocity, and what is the formula it will be arrived when you estimate this thing, is this formula of terminal velocity. Now knowing this formula, we need to calculate this eta. Everything has been given. The terminal velocity is given to be 4 meter per second square, 4 meter per second. The density rho is given as 8050 kg per meter cube. You have a metal ball which has a radius of 5 centimeter, and you have the density of the liquid as 1000 kg per meter cube, and g is 10 meter per second. So everything is given, and then you need to find out the eta. So can you try?
Yes, I can.
Yeah. Now please have a try and tell me what is the answer.
I'm getting 96,000 something value, 96,056.25.
96,000.
It's a very big value, I think.
So I was getting at something. 1.08 something. I don't know whether it is correct.
Oh, it's 5 centimeter. Oh, oh,
Yeah,
I did not convert that to.
yeah.
Okay, that
Right.
should 0.5 centimeters. That would be okay. Still,
There can be some calculation mistake from my side also. Uh,
I'm getting 9.6 after doing this.
okay, fine. So there can be some mistake. I don't know. But I think the message is clear, right? That if you know these
Yes.
things, then you can
Oh, I
calculate.
think I got it. 9 into 4 is one, not 162. That is the mistake, I think. It is 9, correct? 9 VT.
Yeah, yeah. So this is something. Yeah, some mistake is there. Okay, fine. Think so. This is the last question I have. Think so. I think it now this might be helpful for solving the questions of assignment
Yes, it
because
should.
this is
Correct.
the last date might be 18 no 22.
22.
So
Yeah, 22
so
Wednesday.
this is the first session before the assignment submission.
Yes, correct.
Okay, fine. I will try to do now in this way from next week.
Okay, sure.
Okay, okay, fine. Okay,
Okay,
see you
thank
then.
you.
Bye bye. Yeah, thanks.